All right, so this is some milk of magnesia. This is magnesium hydroxide in the solid state, but there's also some that has dissolved. Milk of magnesia, magnesium hydroxide, is something that is slightly soluble in water. And so you can see this solution is cloudy because there's some solid particles suspended in it. Now, you'll also notice that this is kind of bluish, and that's because of the presence of universal pH indicator. The pH indicator basically tells how acidic or basic a solution is, and it changes color accordingly. So what I'm going to do is I'm going to add a little bit of 3 molar hydrochloric acid. Not very much, but it doesn't take much. And what we'll see is that, whoa, look at the color change. But it came right back. All right, so what happened? What happened is it still changing? Maybe a little bit? Well, what's going on? Maybe it will continue changing a little bit. It should get right back to where it was. Anyway, if we look at, say, this chemical equation, we have an initial concentration of magnesium hydroxide that is, well, it doesn't matter because it's solid. So, but initially, before there's any dissolving of the magnesium hydroxide, we had a concentration of magnesium and of hydroxide at 0 molar. Now, when the magnesium hydroxide did dissolve, a certain amount, X of it, dissolved, and that resulted in X magnesium ions going into solution because they are 1-to-1. Also, 2X hydroxide ions went into solution because there are 2 hydroxides per magnesium hydroxide. And so we ended up with a final concentration of X magnesium ions and 2X hydroxide ions. And this is really where we started. When the demo started, we were at this state. And it was at equilibrium. We know it was at equilibrium because this was saturated, and we know it was saturated because there was still solid magnesium hydroxide that had not dissolved. So how much hydroxide was in the solution? Because that's going to tell us the pOH and the pH. Essentially, that tells us how basic the solution was. Well, we know that the KSP for magnesium hydroxide, the expression is going to be the concentration of the 2 products, the magnesium ions and the hydroxide ions, over the reactants, except there are no reactants in the aqueous or gaseous phases, so we leave out the magnesium hydroxide. So we have magnesium ions times hydroxide ions, but because of that coefficient of 2, this is squared. At equilibrium, we have the KSP, which happens to be 1.8 times 10 to the negative 11th, is equal to the concentration of magnesium ions times the concentration of hydroxide ions squared. Now that concentration of hydroxide is, again, 2x, but we still have to square it. So we could eventually solve for x, which is 1.7 times 10 to the negative 4th. And remember, x is the concentration of magnesium ions at equilibrium. So if we wanted the concentration of hydroxide ions, we just multiply that by 2, and here we are at 3.4 times 10 to the negative 4th moles per liter. Now, what is pOH? pOH is the negative log of the concentration of hydroxide ions. It's the negative log of 3.4 times 10 to the negative 4th molar, and that gets us to a pOH of 3.5. Now, if we wanted to find pH, pH is just 14 minus that 3.5, which brings us to 10.5 as our pH. So a pH of greater than 7 is going to be basic. This solution initially was definitely basic. It had a pOH of 3.5 and a pH of 10.5. And that's why the universal indicator was showing as blue. What happened when I added some hydrochloric acid is the following. The hydrochloric acid reacted with the dissolved hydroxide ions and formed water and chloride. So in reacting with the hydroxide ions, we actually took the hydroxide out of the equilibrium. So our 2x became something less than 2x. Our pH actually dropped with the addition of acid. And what this resulted in as we removed a product is it resulted in the equilibrium shifting rightward. Le Chatelier's principle: remove a product and the equilibrium will shift towards the product in response. And just to see how sensitive this whole system was to the stimulus we put on it, well, if we had a 1 liter solution of hydroxide ions, which this is about a liter, and we know that there were 3.4 times 10 to the negative 4th moles of hydroxide per liter. That was our hydroxide concentration. We know that hydrochloric acid reacts with hydroxide in a 1-to-1. I'll tell you that this was 6 molar hydrochloric acid that we used, so I'm going to say that we're multiplying by 1 liter of hydrochloric acid per 6 moles. That's just the molarity of hydrochloric acid. What this gets us to is I needed to use 5.6 times 10 to the negative 5th liters of the hydrochloric acid, or about 0.05 milliliters of this, in order to react with all of the hydroxide ions that were dissolved. So what we saw was all the hydroxide was taken out, which is why the universal indicator changed. It changed to indicate that we had a pH that was actually in the acidic range. That's why we got the color change. However, it did change back. And it changed back to this blue color because the system responded by moving the equilibrium forward by dissolving more magnesium hydroxide. And some of that magnesium hydroxide that had been in the solid state dissolved. That raised our concentration of hydroxide again, and we did get back to a basic pH. So that is the demo, and I hope you enjoyed.